Hello everyone, this is Rami and Alice Parker from the University of Southern California. We are here to represent the research titled Neuromorphic Circuits with Neural Modulation Enhancing the Information Content of Neural Signaling. This research is part of the PURE project, the biomimetic real-time cortex led by Dr. Parker. Here is the outline of the presentation. In the introduction section, we will discuss the significance and the motivation of the research. Then we will show our generated spiking patterns. In the neuromorphic implementation section, we will discuss the actual neuromorphic implementation, including the architecture as well as the transistor level implementations of our model. Lastly, a summary of the main points will be shown in the summary section. The motivation behind the research can be summarized in the following points. Information is transmitted between neurons not only by the absence or presence of a spike. Based on different synaptic input, a neuron can spike differently, as shown in Sardi and Cantor work. The generated spiking pattern carries information about the origin of the stimulus. Dendritic computation, on the other hand, depends on the synapses location and can include dendritic spiking as well as other nonlinear behaviors. It is common to see two neurons behave differently in response to the same stimulus properties. Such behavior indicates dynamic signal processing. Therefore, the primary goal of the research is to create a dynamic model to convert different stimulus properties into different spiking patterns. The importance of the research is to show that spike shapes convey information about the neural stimulation properties that cause the spike. Therefore, our model biomimics dynamic neural behavior. It can do that by converting different synaptic properties into different spiking patterns, as shown in the following block diagram, as well as the capability of mimicking the dynamic neural Threeshot properties. The second important point of the research is the configuration flexibilities, in which it allows for external control. In this section, we will present our results for generating different spiking patterns and our results for the dynamic Threeshot behavior. Our generated patterns are based on the Isaacevich patterns, in which we use the parameter phi-soma to indicate different stimulus shapes, and we use the parameter phi-soma 3 to indicate the dynamic Threeshots. We demonstrate the capability of our model by generating 9 different spiking patterns. In A, the model generates a regular spiking pattern. Here, the neuron fires a train of spikes responding to a set or single pulse of stimulus. In B, our model generates a phasic spiking pattern. In such a spiking pattern, a neuron fires a single spike at the start of an event. In C, our model produces a tonic burst pattern. In such a pattern, a neuron fires a train of bursts with a single or multiple pulses of stimulus. In D, our model demonstrates the capability of generating a single burst stimulus pattern. In E, our model produces a class 1 excitable spiking pattern. In such a spiking pattern, neuron spikes with different frequencies depending on the stimulus amplitude. In F, our model mimics the effect of the sub-Threeshot oscillation pattern. In such a pattern, the neuron generates spike followed by sub-Threeshot oscillation instead of a direct repolarization. In G, the model shows the depolarization after potential pattern. Such neural behavior is correlated with a high voltage gated ion channels inward currents. Our model uses the potassium ion concentration signal to control the depolarization level. In H, our model is acting as an integrator. In such a spiking pattern, a neuron spikes when stimulus with a higher frequency is presented. Here, the spike is generated when the two stimuli are closer to each other, and when the stimuli are further from each other, the neuron became less excitable. And finally, in I, the mixed spiking pattern is shown. Our model generates both spiking and bursting patterns for a single pulse of stimulus. we model the mixed spiking pattern by the activation and deactivation of the calcium ion channels. Next, we show the dynamic three-shot variability by creating dynamic V-soma shapes. In A, the model fires different spiking patterns corresponding to the different V-soma shapes at which V-soma is always greater than the three-shot voltage of the neuron. In B, however, the model generates spiking patterns for the same V-soma shapes only when V-soma is greater than the three-shot voltage signal, showing as a gray color. Here, we show the block diagram of our model. We use V-soma to represent the nonlinear synaptic computations, so that V-soma can be any analog or digital signal. Then, we use a direct correlation to allow V-soma to directly modulate the AIS block to show that even with the simplest modulation function, the number of the generated spiking patterns can be increased. In biological neurons, there are two main compartments, the somatodendritic and the axon hillock compartments. Between these two compartments, there is a region called the axon initial segment, or AIS in short. The AIS is a very specialized region because it represents the site of action potential initiation and the dynamic neural signal processing. Therefore, understanding where the spikes are initiated is essential in understanding how synaptic inputs are converted. Here are a brief biological comparison between the AIS and the soma. The AIS has a smaller diameter, therefore it requires less inward currents to generate a spike. The AIS also has a higher ion channel density. Also, the length and location of the AIS change relative to the soma. Such property is very important in sound localization processing. Last but not least, in pyramidal neurons, for example, the GABAergic interneurons directly modulate the action potentials through the axo-axonic synapses at the AIS region. The schematic diagram and the transistor level implementation of our model are shown here. We are using three comparator circuits. COMP1 controls the three-shot variability and COMP2 controls the activation and deactivation of the voltage-gated calcium channel. On the other hand, COMP3 monitors the voltage across capacitor CA and compare it with the V-soma shape. By comparing these two voltages, a spiking pattern is generated. The capacitor CA models the AIS capacitance. The signal adapt determines the number of the interspikes by controlling the amount of current passing through transistors M16 and M17. Na+ and K+ model the sodium and potassium concentrations respectively. Each of the comparators is implemented using the following circuit, in which the comparators will output a logic 1 for delta n larger than 0 and outputs a logic 0 for delta n less than 0, whereas delta n is the difference between the positive and the negative input terminals of the comparator. In summary, we have presented a neuromorphic model using the 45nm technology node, and all the results are showing using the Cadence Virtuoso simulator tools. We also used the direct correlation as a simple form of modulation to test our modeling hypothesis. We also showed how our resulting patterns are consistent with the Isaac-Kafich mathematical spiking model. And finally, we showed the results of our dynamic three-shot modeling. Thank you for watching, and see you all on July 28th from 10:30 to 11 a.m. for further discussion and Q&A session.